Good afternoon, I'm Mr. Ish. Thank you for joining me. I am bringing here into focus a topic on chemistry which serves as a point of difficulty for students, especially when they start acids and bases. It would look on the surface like an easy topic, but it can be tricky. You have to determine the hydrogen ion concentration, the hydroxide ion concentration, the pH, the pOH, of the scenario that is before you. 0.1 molar acetic acid. It could have been a weak base. Here we're looking at a weak acid. You have 100 milliliters of it, and the acid dissociation constant is 1.8 times 10 to the minus 5. What are some of your relevant equations? How about this? pH is equal to negative log hydrogen ion concentration. There's another one. pOH. pOH is equal to negative log OH. How about this? Remember, you don't have to use all of these. Sometimes you can get the result directly, sometimes you can do it indirectly. How about this? The hydrogen ion concentration times the hydroxide ion concentration is always equal to the Kw, the proton dissociation constant, or the proton constant of water, which is equal to 1 times 10 to the minus 14. That's another equation. All of these can be used directly or indirectly to give you what you need. And there's another equation here, the Ka, the acid dissociation times the base dissociation is equal to the ion product constant of water. If you have this value, because you know this is a standard value, and you know either Ka or Kb, you can determine the other by means of this equation. How do you go about doing this equation, and how do you go about understanding the fact that if you're looking at an acid, how would you determine hydroxide ion or the pOH? Well, you would have an equation which would look like this, and I'm using Ha for acetic acid. It has one proton which can be dissociated. Acetic acid looks something like this. This proton right here can dissociate, and you can end up getting acetate. And then that proton, that right here, which generates this hydrogen ion. And then you know you have a conjugate base, you have an acid. You're looking here at the original acid which will dissociate. All of this comes into play. You can have so many side reactions over here that you can end up generating a bit more than what you would think. This right here can react with water, and you can get a hydronium ion. This right here could pull a hydrogen from a water. You see H2O, it can pluck out this hydrogen, and you can end up reforming acetic acid, and you can end up having an hydroxide ion generate. You see how all of these separate reactions generate? That is why here in the reaction of a weak acid you can also see base developing. All of these things can be calculated, and we will show you how you would do it. And this is very much a high school level topic. How would everything figure out? It would be like this. This is my HA, my acetic acid. It would react with water, because you're doing everything here in water. And what would you get? Because it's a weak acid, you will have arrows in both directions, because it will only partially ionize or partially dissociate. You can have this hydronium develop hydronium ion, and you can have A minus. We can do that, or if you want, you can even look at it in this way: A minus and H plus. Anyhow, you have to determine what your equilibrium expression is, and it's not hard. Ka is equal to, you can look either at this expression right here, or you can look at this. They're both equivalent for the purposes of this video, because water is not included in equilibrium expressions. Pure liquids, pure solids, you don't keep them. You only put the aqueous species into that. It'll equal to your products right here and your acid here on the bottom. What I ended up doing was look at this reaction right here. That right there will give you what you need in terms of this hydrogen ion concentration, and I know it's equal to all of that. Ka is equal to that. How do I determine what those amounts are? Well, I have this reaction here, Ha, I have A minus, and I have H plus, and I have this information right here. You can keep everything here in molarity if you want, or you can put everything in moles. It doesn't matter. I'll keep everything here in molarity. In all instances, this right here is irrelevant, because if I have a start, I have a change, and I have an end. This is 0.1 molar, and I'm starting with 0. This will decrease by x, this will increase by x, this will increase by x, because it will dissociate to a certain amount. Your final amount here will be x and x. This will be 0.1 minus x. You will do your equilibrium expression. You'll have x times x divided by 0.1 minus x is equal to your Ka, which is 1.8 times 10 to the minus 5. When you have a weak base or weak acid, this factor right here can be eliminated, and you can trim your equation down or make it easier and just make it that. You'll really just have x squared is equal to 1.8 times 10 to the minus 5 times 0.1. I have a titration video coming out soon where I'm talking about this shortcut more, and I will leave that discussion for that. You just have to do this computation. Do 1.8 exponent 5 minus, multiply by that 0.1, and you'll square root it. When you square root it, you have 1.3416 times 10 to the minus 3. X is equal to 1.3416 times 10 to the minus 3 molars. But what does this X equal? It equals the concentration of this and that. H plus, it equals the concentration of A minus. This A minus conjugate base is not the same as hydroxide. It isn't. It's the conjugate base that's developing from here. The hydroxide is indeed hydroxide. If this A minus were to react with something like a water molecule, as I was showing you earlier, it can pull out this right here, and you can have an AH and an OH minus. Then OH minus will develop from there, and you're trying to determine the concentration of that. The concentration of this will be dependent on how much of this you have and how much of this you have, because they're equal. Anyhow, what have we determined so far? We've determined the hydrogen ion concentration, so we're good. The hydrogen ion concentration, let's start putting them out right over here, is equal to 1.3416 times 10 to the minus 3 molars. See over here, the volume was irrelevant because we're not titrating this against any base. The volume is irrelevant. The only thing which is relevant is this. How can I determine the pH? Remember, the equation I told you was negative log H plus. I have this value. I'm going to log it. The log of these fractional numbers which are less than 1, greater than 0 are always negative. Hence, the equation has a minus to counteract the minus which will develop. It's 2.87. Your pH is 2.87. How do I develop my hydroxide ion concentration? It's not hard. Think about that equation I told you earlier about the Kw. This everything here is not needed anymore because I need the space now to do the OH and the pOH calculation. The single best way to determine your hydroxide ion concentration is this. Kw, which is equal to 1 times 10 to the minus 14. Why does this work? Why is this true? Because if you look at the dissociation of water, it's H plus and OH minus. If you look at it in terms of a better equation, you have two water molecules. One acts as an acid, one acts as a base. You have H3O plus, and then the other one you have OH minus. They're completely balanced. Plus minus, it's neutral here, neutral here. You have 4 hydrogens, 2 oxygen, 2 oxygens. It works because when you do the Kw for this, it's equal to that. You have OH minus times the H3O plus, which is synonymous with the hydrogen ion, over 1, because waters are not included in the equilibrium expression. Pure liquids and pure solids are not included. It's over 1. All of this is equal to this. Hence, we have this expression which works very well. If I know one, I know the other by means of simple algebra. I know the hydrogen ion has been determined. It was 1.3416 times 10 to the minus 3 times OH minus is equal to 1 times 10 to the minus 14, and then OH minus is equal to that divided by that. It won't be hard. You have your Kw value, which is 1 exponent 14 minus. You divide that by 1.3416 exponent 3 minus, which is your hydrogen ion concentration. You get your hydroxide ion concentration, 7.453 times 10 to the minus 12, which is a very small number, which means you're having very little here, which is true. You're dealing with an acid reaction, you'll have very little base in it. You'll have 7.453 times 10 to the minus 12 molars, and we've figured that out. 7.453 times 10 to the minus 12 molars. Now how do we determine our pOH? pOH is equal to negative log OH. You just take this base concentration and you do the negative log of it, log and then minus. It's 11.12. That's your answer, 11.12. The other way you could have done was this: pH plus pOH is equal to 14. Remember, if you do negative log of this, the negative log of this, you get your 14. And you know that to be true. 1 exponent 14 minus log it, and then minus, you're getting your 14. That's how the pH scale is developed. If you know this, you can do this. pOH is equal to 14 minus pH. What was my pH? It was 2.87. 14 minus 2.87, and you get 11.13. Here I'm off by a little bit, but only because of these decimal values. But everything is good. Hydrogen ion concentration is good, pH is good, hydroxide ion concentration is good, pOH is good, everything is good over here, and you saw how everything came about. Everything could have been here with a weak base like ammonia, and then you would be working on the base side up to the acid side, and you do all your determinations. As the very last digression for this video, simply because I mentioned it earlier, was this Ka times Kb is equal to Kw. If I know Ka, I can do Kb. Kb is equal to Kw divided by Ka, which is equal to 1 times 10 to the minus 14 divided by your Ka. 1.8 times 10 to the minus 5, and your Kb value, which you would use if you're looking here at a weak base, it would be 1 exponent 14 minus divided by 1.8 exponent 5 minus, and you have 5.55 repeating times 10 to the minus 10. And there are no units over here for this you have to be worried about. So we've determined actually Kb, pOH, hydroxide ion concentration, pH, and the hydrogen ion concentration all from a weak acid, and that's how you would do this. Thank you for watching.